So, have you ever watched a sci-fi blockbuster and wondered if Hollywood's absolute favorite space-time shortcut is actually, possible? I mean, we've all seen ships sip across the galaxy in the blink of an eye using those glowing cosmic tunnels. But what does actual rigorous physics have to say about this? Can we actually build a Stargate? Or is it purely cinematic magic?
Welcome to this explainer. Today, our goal is to completely demystify wormholes by separating the fiction from the hard, undeniable mathematics of general relativity. We're going to look at what the math actually permits, the completely bizarre physical requirements to make these portals work, including a dive into the mind-bending reality of negative energy and the absolute logical nightmares that arise if we try to use them to manipulate time. All right, let's jump right into Section 1, the space-time shortcut.
Okay, let's ground this by establishing what a wormhole actually is at a foundational geometric level. To visualize the topology, picture the universe as a two-dimensional sheet of paper. If you fold that paper in half so two distant points touch, a wormhole is basically the puncture straight through that folded space. But in our three-dimensional reality, it's significantly more complex. We're talking about two spherical mouths connected by a highly curved passage known as the throat. It's a hypothetical topological feature of spacetime that connects two completely disparate points, meaning it could connect different locations in space, different points in time, or even both. By stepping into one spherical mouth, you traverse the throat and instantly step out of the other mouth millions of light years away. You're completely bypassing the speed limit of light because you aren't actually moving through the intervening space. It's the ultimate cosmic cheat code.
Moving on to Section 2, let's look at the famous Einstein-Rosen bridges.
Now, looking at the timeline of discovery, you might just assume Albert Einstein came up with a whole concept from scratch. But the very first mathematical hint was actually discovered by Austrian physicist Ludwig Flamm way back in 1916. Flamm was reviewing Karl Schwarzschild's solution to Einstein's field equations and realized, hey, the math perfectly allows for a bridge connecting two regions of flat spacetime. Then in 1928, Hermann Weyl proposed the idea of one-dimensional tubes modeling electromagnetic field lines. It actually wasn't until 1935 that Einstein and his colleague Nathan Rosen formalized this geometry into what we rigorously call the Einstein-Rosen Bridge. And here's a totally fun fact for you. Einstein didn't even invent the term wormhole. That incredibly catchy name was coined decades later, in 1957, by theoretical physicist John Archibald Wheeler.
But there's a massive catch with those original Einstein-Rosen bridges, which are also known as Schwarzschild wormholes. That original Schwarzschild geometry is entirely useless for travel. Why? Because the mathematics dictate that it is inherently, violently unstable. The gravitational tidal forces inside the throat are so immense that the structure would pinch off and collapse inward toward a singularity almost instantly. I mean, it collapses so incredibly fast that not even a photon moving at the speed of light could cross from one mouth to the other before being utterly crushed. So to actually use a wormhole, we need a fundamentally different structural design, a traversable wormhole.
Which brings us to Section 3, the exotic matter problem.
So how exactly do we get that traversable version, the kind famously explored by physicist Kip Thorne in the 1980s? Well, that brings us to our absolute biggest engineering hurdle. To keep a wormhole from collapsing on itself, you have to find a way to hold its throat open. Normal matter simply cannot do this. Its positive mass creates a gravitational pull that only accelerates the curvature and collapse of the throat. To fight that immense gravity, you need a very specific, highly unusual substance called exotic matter. Now, it's crucial to understand this isn't just antimatter, which still has positive mass. And it's not dark matter either. This is a hypothetical material that actually possesses negative mass and negative energy density. It would essentially exhibit anti-gravity properties, providing this immense outward pressure to counteract the collapse of the space-time throat.
Now, you might be thinking, negative energy? Okay, that sounds like pure science fiction. But let's actually ground this concept in verifiable physics. According to the Casimir effect in quantum field theory, the energy density in certain regions of a vacuum can genuinely be negative relative to ordinary empty space. Imagine two perfectly uncharged conductive plates placed just micrometers apart in a vacuum. Virtual particles are constantly popping in and out of existence all around them. Because the plates are so incredibly close, longer wavelength virtual particles physically can't fit between them, meaning there are literally more virtual particles pushing from the outside than pushing from the inside. This restriction creates a very real region of localized negative energy density between the plates. While quantum field theory strictly regulates how long and how intense this negative energy can be, physicists like Stephen Hawking and Kip Thorne have argued that these very real, macroscopic quantum effects might just make it mathematically possible to construct and stabilize a traversable wormhole. The underlying math actually holds up.
Okay, section 4. This is where things get truly weird. Time machines and multiverses.
All right, so if we assume we can eventually harness enough of that exotic matter to stabilize a portal, the theoretical consequences become absolutely mind-bending. Back in 1988, Kip Thorne and his colleagues basically wrote a step-by-step theoretical manual detailing how to build a time machine using a traversable wormhole. Because time connects differently through the internal throat of the wormhole than it does in the external universe, you can exploit relativistic time dilation. Step 1, you take one mouth of the wormhole and accelerate it to a significant fraction of the speed of light. Now, let's just acknowledge the sheer engineering impossibility here. This would likely require the energy output of an entire star just to move it. But theoretically, step 2, you bring that accelerated mouth back to its stationary twin. Because it was moving so incredibly fast, the accelerated end has aged significantly less. So, step 3, an observer who enters the younger end will step through the throat and exit the older end at a time when it was the exact same age. You've effectively created a closed time-like curve, a literal shortcut to the past.
But general relativity places a strict, uncompromising boundary on this time machine. You cannot use this setup to travel back to a time earlier than the exact moment the wormhole was originally converted into a time machine. Think of it not as a magical DeLorean that lets you drive anywhere backward along a timeline, but more like a permanent temporal tunnel. The tunnel only goes as far back as the moment the entrance was constructed. So if you successfully build and link this temporal bridge in the year 3000, you can never, ever use it to go back to the year 2999.
Setting that limitation aside for a second, this setup naturally begs the ultimate question of causality. What if you go back through this wormhole tunnel and do something that prevents the wormhole from ever being built in the first place? This is the classic grandfather paradox, a logical nightmare that threatens the foundational cause and effect relationship of the entire universe. So how does the physics of the cosmos handle this?
Well, physicists have rigorously explored this paradox. Stephen Hawking proposed the chronology protection conjecture, suggesting that nature categorically prevents paradoxes by just destroying the wormhole. The mechanism for this is fascinating. Virtual particles could circulate through the time machine continuously. Because they go back in time, they loop through the exact same space infinitely, creating a destructive positive feedback loop. Sort of like when you put a microphone too close to a speaker. The energy would amplify to infinity, incinerating the wormhole in a fraction of a second before anyone could ever use it. But a completely different and deeply fascinating resolution comes from physicist David Deutsch. In 1991, he demonstrated that quantum theory actually allows for consistency in these time loops. How? By invoking the many worlds interpretation of quantum mechanics. Deutsch's math suggests a particle returning from the future wouldn't return to its original timeline to cause a paradox at all. Instead, it would slide into a parallel universe. Under this framework, a time jump through a wormhole could actually be an Everett-Farn, a direct bridge between parallel realities where all possible outcomes safely play out.
Physicists have taken this to incredible extremes to test these theories. In 1997, Matt Visser explored highly complex configurations called Roman rings, which are named after physicist Tom Roman. Imagine multiple wormholes arranged in a symmetric polygon. Visser studied this because arranging multiple wormholes was a clever attempt by physicists to bypass the single wormhole paradoxes and basically cheat that destructive feedback loop Hawking talked about. Visser proved this intricate configuration could theoretically still act as a time machine, though he noted this mathematical exercise really just highlighted deep, unresolved flaws in our understanding of classical quantum gravity rather than proving causality violation is a given. It just goes to show how deeply scientists probe these extreme theoretical geometries, constantly hitting new roadblocks as they try to push the very limits of known physics.
So, you might be asking, why does mathematically exploring these incredibly distant, seemingly impossible macroscopic structures actually matter to us? Well, because the fabric of reality is far wilder up close. Let's look at the quantum foam hypothesis. At the incredibly tiny Planck scale, which is a scale billions of times smaller than a single proton, spacetime is not smooth. It is completely turbulent, constantly boiling and bubbling. At this incomprehensibly small level, tiny, microscopic wormholes might be spontaneously blinking in and out of existence all around us, right this very second, woven into the very fabric of the room you're sitting in.
Which leaves us with this final, truly provocative thought. If these tiny, natural wormholes were popping into existence during the ferocious energy of the Big Bang, some physicists suggest cosmic strings, which are essentially one-dimensional topological defects with immense negative mass, could have threaded through them, holding them open.
And if that happened, the rapid expansion of cosmic inflation might have stretched these microscopic oddities to massive, macroscopic sizes. Could one of these primordial stargates be floating out there in the deep universe right now? Just an ancient relic of the Big Bang, waiting to be found? While Hollywood certainly stretches the truth for the sake of a good movie, the actual mathematical physics of our universe is far stranger and far more wondrous than fiction. Thanks for joining me on this explainer.